This is section 2.6, limits at infinity and horizontal asymptotes. Okay, so we're on page 126, limits at infinity. Page 127. All right, so limit x approaches infinity of f of x equals L. So x gets bigger and bigger and bigger. So you're plugging in numbers like 100, 1,000, 1,000,000, 1 billion, and trillion to the y values approach any limit. Okay, so here are some examples. Limit as x approaches infinity as we go way out to the right, the y values approach L. It could be from above, it could be from below, it could even squiggle on like so. Okay, in case you're wondering, you may have heard there's a rule that says an asymptote is a line that the graph approaches but doesn't touch. Take out the doesn't touch. It's allowed to touch, especially for horizontal asymptote. Okay, it doesn't touch a lot, okay, but that's not true in general. Okay, so this is considered still an asymptote. All right, so we can go approach infinity. We can also approach negative infinity. So I go as far as I want to the left. Okay, so on page 128, limit as x approaches negative infinity of f of x equals L. So I go way out here, we approach a limit, or it could look like this. And that leads us to a horizontal asymptote. So y equals L is a horizontal asymptote if either limit as x approaches infinity of f of x is L, or limit as x approaches negative infinity of f of x is equal to L. A key one that you'll probably want to know is the inverse tangent. You're going to get a lot of that in Calc 2 and a little bit in Calc 3. Inverse tangent looks like this. So as x approaches infinity, y approaches pi over 2. And if x approaches negative infinity, y approaches negative pi over 2. So limit as x approaches negative infinity of inverse tangent of x is negative pi over 2. And limit as x approaches infinity of inverse tangent of x is positive pi over 2, as you can see over here. Okay. Okay, here's the graph of y equals 1 over x. It's on page 129. Okay, so when x approaches infinity, y approaches 0. So I plug in 1,000,000, 1 billion, 1 trillion, 1 over that is practically 0. And limit as x approaches negative infinity of 1 over x is also 0. I plug in negative 1,000,000, negative 1 billion, negative 1 trillion, this fraction approaches 0. Slightly negative, but it still approaches 0. Okay. In fact, we can say in general, if I have 1 over x to the r, where r is any rational number, then limit as x approaches infinity of 1 over x to the r is 0. So if I have 1 over x squared, x cubed, x to the 4th, or x to the 2/3, or whatever, this thing still approaches 0. All right. E to the x on page 132. E to the x looks like this. So limit as x approaches negative infinity of f of x is 0. And they make a little table of values here. It's like a negative 10, you're already at 0.00005, so it's getting real small. And as x approaches infinity, y also approaches infinity. So the limit as x approaches positive infinity of e to the x is infinity. Okay. Okay, so here are the homework problems, 2.6. So 3 to 10 all, 15 to 37 odd, 47 to 51 odd, 61, 63, 65. So let's see if we can get those to you now. Page 137. 3, 4 starts down there, but it continues here. 5 through 10. So this F is even there. Maybe looking up to 65, it looks like. Find the limits. Small over here. Over here. And then the ones over here. Up to 65. Okay. Okay, so we have 3 through 10 all. So I'll try to show you the evens. All right, so 4. What's the limit as x approaches infinity and negative infinity? So as x approaches infinity, y approaches 2. On this side, -1. So a is 2, b is -1. Limit as x approaches 0. Limit as x approaches 2 from the left. Limit as x approaches 0, both sides, -infinity. Limit as x approaches d, x approaches 2 from the left. X approaches 2 from the left, y approaches -infinity. So d is -infinity. E, limit as x approaches 2 from the right is positive infinity. And then the asymptotes. Asymptotes. So we have y equals 2, y equals -1, x equals 0, and x equals 2. Looks like. Okay. All right, sketch the graph of the following. Okay, 6. As x approaches 2 of the function, we approach infinity. It's two-sided. So on two sides, we go to infinity as x approaches 2. As x approaches -2 from the right, we approach infinity. If we approach -2 from the left, we go down to -infinity. Limit as x approaches -infinity of the function is 0. So I go way out here, we approach 0. As x approaches positive infinity, we also approach 0. And f of 0 is 0. So here's the graph for number 6. 8. As x approaches infinity, f of x approaches 3. So here's 3. Limit as x approaches 2 from the left of the function is infinity. So we approach 2 from the left, we go to infinity. When x approaches 2 from the right, we go to -infinity. Okay. And then it says f is odd. If f is odd, we have symmetry with respect to the origin. So this bounces over here. This thing reflects and ends up looking like this. So that's number 8. 10. Limit as x approaches 3 of f of x is -infinity. So we approach 3 on both sides, -infinity. Limit as x approaches infinity of f of x is 2. So we go like so. And f is even. Okay, so if I have this, I have symmetry with respect to the y-axis. So I just do the mirror image. I got that, and I got that. Okay, I guess I should put an arrow here. Okay, 15 to 37, compute the limits. So there are certain tricks to be had for that. Okay, 3x minus 2 over 2x plus 1. If for ratios, superficially, this is quote unquote infinity over infinity. Big number divided by big number. We plug in a billion. Okay, this is first degree. This is first degree. The trick is to divide top and bottom by x, because this is first degree. This is first degree. So 3x minus 2 over x divided by 2x plus 1 over x. And then I divide. So 3x divided by x is 3 minus 2 over x. This is just 2. That's 1 over x. And now when x gets super big, that approaches 0, that approaches 0. So I have the limit as x approaches infinity of 3 minus 0 divided by 2 plus 0, 3 over 2. Okay. This is how you do it analytically. But if you want something quick and dirty superficially, remember when x gets super big, -2 and a +1 drop into insignificance. You can pretty much ignore it and just say 3x over 2x, that's 3 over 2. Okay. If x is a billion, 3 billion minus 2, that's practically 3 billion. 2 billion plus 1, that's practically 2 billions there. So the ratio is 3 over 2. Okay, 23. Now, this is third degree. This is kind of like third degree because there's an x to the sixth underneath the square root, except there's a 1 in the way. Okay, the trick for that one is, so this is sort of like third degree. I divide top and bottom by x cubed. So I divide this by x cubed, and I divide this by x cubed in the form of x to the sixth underneath the radical. So this is still dividing by x cubed. So this is a valid step. X cubed outside the radical is x to the sixth inside the radical. Then I divide, limit as x goes to infinity, 1 over x to the sixth plus, that's 4, divided by 2 over x cubed minus x cubed over x cubed is 1. And now when x gets big, this is nothing, this is nothing. So I have the square root of 0 plus 4 over 0 minus 1. That's 2 over negative 1. Final answer is negative 2. Okay, for 27, I wasn't going to do it now. I'll just give you a hint. Multiply the numerator and the denominator by the conjugate. So that's a hint to get 27 started. So multiply by radical plus 3x divided by the same thing and see where it takes you. Okay. (31). Let's see, this is fourth degree, this is third degree. So if the degrees are different, what should I do? Okay, you could actually divide by either x to the fourth or x cubed. Let's divide top and bottom by x cubed to see what happens. So divide by x cubed in red, divide by x cubed in red. That's x minus 3 over x plus 1 over x squared. The key thing is all these fractions tend to 0. 1 minus 1 over x squared plus 2 over x cubed. Now when x gets super big, a million, a billion, a trillion, that's nothing, that's nothing, that's nothing, that's nothing. So I basically have x. And what happens when x gets big? X gets big. So the answer is infinity. Intuitively, fourth degree beats third degree in the long run. So this thing behaves almost like x. 33, the key to this one is to factor out the common factor of x squared. X squared times 1 plus 2x to the fifth. Okay, now if I plug in a negative big number, this is a large positive. This whole thing's a large negative. So large positive times large negative, negative infinity. 35, limit as x approaches infinity, arctan e to the x. When x gets big, this gets big. And we said arctangent of a super big number approaches pi over 2. I mean, here's the graph of inverse tangent. Okay. So we have pi over 2 for that one. Okay. (47) y equals 5 plus 4x divided by x plus 3. Vertical asymptote, x equals negative 3. Horizontal asymptote, first degree, divide top and bottom by x. So limit as x approaches either plus or minus infinity, so I put plus or minus. 5 over x plus 4x over x is 4, divided by 1 plus 3 over x. Okay, so when x gets real big, either positive or negative, that's 0, that's 0. So I have 0 plus 4 over 1 plus 0, which is 4. So my horizontal asymptote is y equals 4. Okay, 51, y equals x cubed minus x over x squared minus 6x plus 5. This is third degree, this is second degree. I'm not going to have a horizontal asymptote. Okay, let's do some factoring. This is x times x squared minus 1, which is x times x plus 1, x minus 1. This is x minus 5, x minus 1. Cancel out the x minus 1s. Okay, so x equals 1 is not a vertical asymptote. You're going to have a hole, but it's not an asymptote. X equals 5 is going to be an asymptote. So vertical asymptote, x equals 5, no horizontal asymptote. Okay, then 61, 63. Find the limits as x approaches infinity and x approaches negative infinity. Use this information together with intercepts to give a rough sketch of the graph. Okay. So here we go. So the zeros are 3, -1, and 1. So -1, 1, and 3. All right, then what happens when x goes to infinity and negative infinity? This is always positive. This is always positive, unless I plug in 1 or -1. Okay, so if x is big, 3 minus big is negative. So it drops to negative infinity. If I plug in, let's say, -1,000,000, positive, positive. 3 minus a -1,000,000 is positive, so it shoots to positive infinity. Okay, so right now for my graph, I have this going up, this going down. And what about the rest of it? Well, if I plug in any number over here, it's going to be greater than 0, right? Like if I plug in 0, that's positive. If I plug in 2, that's positive. So these will go up and down, up and down. So there's the entire graph. F of 0 is greater than 0. F of 2 is greater than 0. So I have that. Okay. So 1 plus x squared and 1 minus x to the fourth are always non-negative. Okay, I have one last problem, but it's going to take a little while to develop this. 65. Use the squeeze theorem to evaluate limit x approaches infinity of sine x over x. Skip part B, which involves a graphing calculator. Okay, so something I skipped back on page 101 is something called the squeeze theorem. We didn't need it then, but we need it now. Okay, so back on page 101, section 2.3, squeeze theorem. You have 3 functions, f, g, and h. F is less than or equal to g, less than or equal to h. The 2 extreme functions, limit as x approaches a of f of x, equals the limit as x approaches a of h of x is equal to L. So the top and lower function approach the same limit. Therefore, this function, which is squeezed between the 2, also has to approach the same limit. It's called the squeeze theorem. And here's the picture. 3 functions, f, g, and h. F is less than or equal to g, is less than or equal to h. The smallest function, f, as x approaches a, approaches the limit L. Likewise, the top function, h of x, as x approaches a, approaches L. G is squeezed between the 2, so it also has to approach the same limit. It's called the squeeze theorem. Sometimes it's called the sandwich theorem or the pinching theorem. Okay, so anyway, getting back to where we were in 2.6. I'm going to answer the question now about the squeeze theorem. 65. Use the squeeze theorem to evaluate limit as x goes to infinity of sine x over x. So here's what we do. Okay, from trig, I know that -1 is less than or equal to sine x, less than or equal to 1. That's always true. Then I divide everything by x. Okay. We're going to let x approach infinity, which means x is positive, so I don't have to change the inequality. Okay, what happens to 1 over x as x gets big? That approaches 0. What happens to -1 over x as x gets big? That approaches 0. Therefore, sine x over x, which is squeezed between them, also approaches 0. So limit x approaches infinity of 1 over x is clearly 0. Plug in a super big number. Limit x approaches negative infinity. Sorry, x approaches infinity of -1 over x is also 0. So therefore, any function squeezed between them, like sine x over x, so limit x approaches infinity of sine x over x is also equal to 0 because it's squeezed between 2 functions which both approach 0. Okay, problem's finished. There's a picture. Here's 1 over x. Here's -1 over x. And sine x over x is stuck between them. It was squeezed. So it kind of looks like a sine-like function, but it dampens as x gets bigger and bigger. So it bounces up and down, but it's squeezed between these two functions. So it also has to approach 0. Okay. All right, so that's section 2.6.